This is section 2.5, part B, and we're going to start looking at some other types of things that can happen with our equations when we graph them. Start looking for some more patterns, so to speak. So far, as we just mentioned, all of the problems that we have done have factored into linear factors, in fact, unique linear factors, not repeated ones. In this section B, I'm going to ask myself the question, what happens if I have repeated linear factors? Okay. Let's take a look at this first one. And if I wanted to find the x-intercepts, I would, as always, set the y or f of x value equal to 0. And I'm actually going to do just a little bit more with this one. I'm going to write this out, not just as x minus 1 squared, but x minus 1 times another x minus 1, which is what, of course, it really means. So if I set each factor equal to 0, I'm going to get an x equals negative 2, and then I'm going to get x equals 1 twice. When that happens, we call that a solution of multiplicity 2. And I'm just going to use capital M for multiplicity. I'm going to say the multiplicity of that is 2. We want to investigate what multiplicity does to the shape of our graph. So, first of all, I know I've got negative 2 as one of my zeros, or x-intercepts, and 1 as another one. I'm really interested in that one because of its multiplicity. And let's just talk a little bit about degree here. This would be an x to the first. And this one's going to get an x squared in it. So I'm not going to multiply it all out, but I can kind of see that if I did, it would end up having an x cubed, or be third degree. So my degree is going to be 3. I've already seen there are 2 x-intercepts. That's kind of different, a little bit different than the ones we looked at in the last video, right, where the degree always matched the intercepts, but that's because of the multiplicity. And from there, I'm actually going to use Desmos to help me out. So I've got Desmos screen back here. Here's the first graph that we just were looking at. Here is that 0 at negative 2, the one we found by hand, as well as 1. But look at what happens. Up till now, every time we've gone through a 0, we've literally gone through the x-axis. Or in other words, our graph has cut through the x-axis. Look what happens at the 0 of multiplicity 2. Instead of cutting through my x-axis, the graph kind of bounces off the x-axis and goes back up again. Okay? That's typical behavior, and it is in some way associated with multiplicity. I'm not quite yet ready to make a general statement, but watch for that cutting through versus bouncing off the x-axis. Right? All right. I'm not going to draw all of these by hand. You can sketch them from the screen if you want to. But let's just go ahead and say, for this particular one, if I were to draw it, to finish this one out since I've started it, this was the shape I got. And specifically, I noticed that right at that 0 of multiplicity 2, I had this sort of a bounce-off effect on the x-axis. And we're going to watch for that in some of the other graphs as well. Just to finish my little box here, I do still have 2 turning points. There's one maximum and one minimum. So right now, that 1 less than the degree still kind of seems to be holding. And then the end behavior, down on the left and up on the right. We talked last time about how the degree and the end behavior essentially go together. Since this is a degree 3 polynomial, I would expect the end behavior to be like y equals x to the third power. And you remember we studied those back in section 2.1. This is that wave. So down on the left, and yeah, this one goes down on the left also. Up on the right, up on the right. So my end behavior is as it should be, down to the left, and up to the right. Okay. All right, I'm not actually going to take the time to write that out for every single one of these. You can fill them in if you like. But what I would like to do instead is let's just take a look what we're doing, and then we will take a look at what happens using the Desmos graphs rather than painstakingly filling this all in by hand. So, when I go to number 2, notice it's almost the same equation, except this time my x minus 1 is to the third power. So if I were to set that equal to 0 to get the x-intercepts, there would actually be 3 factors of x minus 1. So I'll get x equals -2, and then I'll get x equals 1, but I'll get it 3 times. So I'm going to say multiplicity 3. Let's look at that one. Here's that 0 at -2. Not much is changing with that one, still cuts through. But look at what happens now at 1. It no longer bounces off. It actually cuts through, right? It goes from negative values of y to positive values, but it kind of flattens out just a little bit right where it cuts through the x-axis. Kind of should remind you a little bit of that wave that the x cubed graph has, right? So with a multiplicity 3, we're back to the graph cutting through the x-axis. And I won't transfer all these drawings. I'm just going to mention here the graph cut through. The x-axis. On the next page, I'm going to continue with the same basic setup. And you will notice that we have a 4th power and a 5th power. So let's take a look at those. With the 4th power, x equals 1 is going to have multiplicity 4. There it is. Notice we're back to bouncing off. And with the 5th power, so a 0 of multiplicity 5, we're back to the graph cutting through the x-axis. So here I'd have x equals -2 and x equals 1 with a multiplicity of 4. This one bounced off. And here I'd have x equals -2. And this time my x equals 1 had a multiplicity of 5. That was that last one we just looked at. And that one, the graph cut through the x-axis. What I'm hoping that you're noticing is there's an even-odd relationship here. When we have even multiplicities, we get the bounce-off effect, right? Multiplicity 2, we bounced off the x-axis. Although we didn't draw it, multiplicity 4, again, we bounced off the x-axis. So the even multiplicities cause that bounce. The odd multiplicities, like 5 and 3, our graph was still cutting through the x-axis. So, to kind of summarize that, down at the bottom here of the page, 107, what I'm saying is if we have a 0 with even multiplicity, the graph is going to bounce off the x-axis. At that 0. But if our 0 had odd multiplicity, then the graph does cut through the x-axis at that 0. All right, so that kind of takes care of how does the multiple repeated linear factors work. They give us zeros with different multiplicities, and how they behave depends on the even versus the odd. The next section, section C here, is going to talk about what happens when we can't factor everything into linear factors. Sometimes when we start factoring, we end up with some irreducible or prime quadratic factors. Like, for example, this one right here. This is in its factored form, and x minus 2 is one of the factors. But the second factor is this quadratic. And if you think about it, we're not going to be able to factor that. A sum of 3 and a product of 1 is not going to work. So that's as factored as this one gets. Let's think about our x-intercepts. We'd have x minus 2 equals 0, and we'd have x squared plus 3x plus 1 equals 0. So x equals 2 is going to be one of my zeros, so 2 here is one of the x-intercepts as well. And then this one, because I can't solve by factoring, I'm going to have to go ahead and fall back on the quadratic formula on that one. So let's see. I'd have minus 3 plus or minus the square root of 3 squared minus 4 times 1 over 2 times 1. Let's see, that would be 9 minus 4 is 5 under that radical. So I do get 2 x-intercepts. If I'm going to plot them on my graph, though, I probably should get some decimal approximations. Let's see, negative 3 add square root of 5 divided by 2 is about negative 0.38. And negative 3 subtract square root of 5 divided by 2 is about negative 2.62. So those are my other x-intercepts around here and about there. Notice, by the way, this is a cubic function. This would have degree 3. I'm not going to multiply it all out. But if I think about the highest power in each set of parentheses, x to the first times x to the second would give me an x to the third. So this is degree 3, and I just found 3 x-intercepts. That's all there can be, right? All right, I want to predict what this one's going to look like before I look at it on Desmos. We'll hold off on the turning points for a minute, but let's think about the end behavior. Again, degree and end behavior go together. So the end behavior is going to be like y equals x to the third, which is that wave. So it should be down to the left and up to the right. So keeping that in mind, I think I can do a pretty good job of actually predicting what this is going to look like. I need to start down to the left. I'm going to come up and cut through that first x-intercept. Come back down and cut through the second one. Dip down, come back up, and cut through the last one. And notice my end behavior down to the left, up to the right is consistent. So other than the fact that I don't really know how high or low to go for the maximum and the minimum, that should be a pretty good prediction of what this looks like. Here it is. And it really wasn't bad. Right? There's our 3 x-intercepts as predicted. And my graph is exactly the shape we expected it to be. All right. Let's see here. How about this one? This is another cubic polynomial. I'm once again going to say if x minus 2 is 0, then I should get an x-intercept at 2. And then I have x squared plus 3x plus 4 equals 0 from my second factor. So again, I don't think that factors. Sum of 3 product of 4 is not going to do anything. So let's try quadratic formula one more time. All right, I've got negative 3 plus or minus the square root. And under my radical, I have 9 subtract 16. So I have negative 7. As soon as I see a negative under the radical, I know that these are zeros, but imaginary numbers don't appear on graphs, so they won't be x-intercepts. Let me just finish this. I can say the square root of negative 1 is I. So I can write it as I square root 7 there. And I'm going to say these are some imaginary zeros for my function f. But because they're imaginary, they don't give me any x-intercepts. Okay. So that x equals 2 is the only x-intercept I actually get. All right, let's think this through. Once again, I have an x to the first times an x squared. So this will be degree 3 again. I only found one x-intercept. And my end behavior should be like x cubed again. So it should be that little wave type again. down to the left, up to the right. All right. Based on the information that I have, really about all I could do would be to say go down here, cut through, and come up. But I'm a little suspicious that there might be more going on. So let's take a look at a Desmos graph before we actually try to draw this. Here it is. And look what happens. There is a maximum and a minimum. There's actually two turning points. And they are below the x-axis. So they don't give us any intercepts, but we still get that maximum and minimum like we saw in the previous problem. So I'm going to kind of just sketch what I see here more or less. There's my picture. Still two turning points, but because they were below the x-axis, they didn't contribute to the x-intercepts. All right, so that's kind of what can happen with the irreducible quadratics. I'm actually going to skip the one on number 3 here. It's really no different than things we've already done. So example 3 at the top of page 109, I'm going to skip that over. But let's summarize here at the bottom of page 109 what we kind of figured out here. With an irreducible quadratic, factor, if it has real zeros, right? If we set it equal to 0 and we get real values, then we do get some more x-intercept. So real zeros, these are x-intercepts. If we get imaginary zeros, there are no new x-intercepts. All right, we've got one more kind of set of functions to look at, to see one more pattern, and then we're going to be ready to put all this stuff together in a couple of examples. All right, in section D, I want to look at the effect of a numerical GCF on the graph of a polynomial. And again, it says find the x-intercepts by hand, and then we're going to graph using Desmos to sort of see the pattern. So these are not factored for us, so for the first time here we ought to factor again by ourselves, so darn. Let's go ahead and do that. For terms, so I am using grouping. See, I can factor out an x squared, which makes that x plus 1. And then over here, I'm just going to factor out a negative 1, which also gives me x plus 1. So factor out that x plus 1, and that gives us x squared minus 1. Okay. X squared minus 1 is a difference of squares, so I can factor that a little bit further. This will be x plus 1, x minus 1. And so notice, I'm going to get x equals negative 1 twice. So that's going to have a multiplicity of 2. And then I'll also just get x equals positive 1, but that's just once. So that would have a multiplicity of 1. So negative 1 and positive 1. All right. This is degree 3 again. So the end behavior should be like the x cubed graph, down to the left and up to the right. So I think I kind of know what to do here. The multiplicity 2 is going to be a bounce off, right? So I'm going to Multiplicity 1 is going to be a cut through. So if I went to graph this, I would start down to the left. At negative 1, I'm going to bounce off, and I'm going to come back up and cut through. So I think it has to look something like that. Let's check. There it is. And I'm actually going to, well, just leave it like that. There's that bounce off at negative 1. And there is the cut through at positive 1, just like we expected. All right, the next several problems are just going to be the same exact polynomial, but with a common multiple running throughout it. So you'll notice here in number 2, if I factored out the 2, I would have the same polynomial as the one I just finished working with. So I can actually steal my factoring from over here. So it's the same thing, but with this GCF of 2. It should have the same x-intercepts as before. So the basic shape shouldn't change, but let's just take a look at the graph to see what that multiplier of 2 does. I've even shown it factored out right here. And I actually am going to zoom in just a little bit. Okay. The original graph is in red, and then the multiplier of 2 graph is in blue. And again, notice the x-intercepts haven't changed. They're still at plus and minus 1 for both of them. But the blue graph, the one with the multiplier of 2, is being stretched vertically. If I look here at the y-intercept, notice the red graph had a y-intercept of negative 1. The blue graph is exactly double that. If I look here at the minimum, again, the y value on the red graph is doubled to give the y value on the blue graph. So same x-intercepts, same basic shape, but we have this vertical stretch going on. By a factor of 2. On the next page, I'm going to continue with the multiples of the same polynomial. Here you'll notice that I could factor out a negative 1. And when I do, I'm back to that same old polynomial that we started with again. So again, I could steal its factored form that we've already worked out. So once again, I have the same x-intercepts. But my GCF this time is negative 1. If you're already thinking back to some other things that we did when we had negative multipliers, that's a good thing. So you may be already predicting what's going to happen. I hope so. But let's take a look. So there, the red graph again was my original. Here's the one with the GCF of negative 1. And notice probably what you predicted. It just reflected it across the x-axis, turned it upside down, if you will. So a negative multiplier does reflect or flip the graph. And the last one, I could actually factor out a -3 here. At which point I'm back to my same original again. So once again, I'm just going to steal the factoring that we already worked out. So back to the same x-intercepts. But this time with a GCF of -3. So this is kind of a combination of number 2 and number 3. The negative should reflect it, but then the factor of 3 should give it a vertical stretch. So I should see a reflected graph with a vertical stretch. So there's my original again there in red. Here's the one with the multiplier of -3. It has been reflected, right? Notice instead of going down to the left, it goes up to the left, and so on. There's those same x-intercepts. But notice that in addition to being reflected, we also have that stretch. Look at the y-intercepts here, right? The original had a y-intercept of -1. It's been reflected, so it's now positive, but it's also been multiplied by 3. So reflected and stretched. All right, so at the bottom of page 111 here, just to kind of summarize our conclusions, what does a numerical GCF do to the graph of a polynomial? It provides a vertical stretch, and if the multiplier is negative, graph reflects across the x-axis. All right, we will stop there for now, and I'll finish out this section in one last video.